Good day and welcome back for the fifth and final installment of our discussion on continuity. So as a reminder, in this video we are going to focus in on problem 2 of an associated class worksheet that you can find posted in Canvas. And as I've mentioned previously, if we happen to have been meeting in person, I would have passed the worksheet out, had you formed groups of 2, 3, 4 students, and we probably would have spent 20-25 minutes working on this worksheet. And then I would answer some questions and post solutions on Canvas. And we're going to try to follow that exact same model. So hopefully you've pulled up the worksheet, you've spent 20 to 25 minutes thinking about it, and now we are going to discuss problem number 2. And if you haven't pulled up the worksheet, if you haven't spent 20 to 25 minutes working on this, then I suggest doing so. Remember, you take out of this process what you put into this. I want you to be as engaged as possible, really given our current scenario. So for this question number 2, we're given a function. It's defined to be one thing to the left of minus 1, something else when we are larger than minus 1, and then even a third thing at minus 1. And what we would like to do is determine what are the values of this constant a that's used to define our function p, where the limit as x approaches minus 1 exists. And the key observation to make is the limit as x approaches minus 1 of a function will exist when the limit from the left is equal to the limit from the right. So this is true precisely when the limit as we approach minus 1 from the left is equal to the limit as we approach minus 1 from the right. So we have two limits that we need to calculate, and whatever values we get from them, we need to force them to be the same thing. And that might require us to pick a specific value of a. So if we're thinking about approaching minus 1 from the left, note that means we are smaller than minus 1. So we are going to use the function x squared plus a. So we're just kind of reading out what our piecewise definition of the function tells us. So this would be the limit as x approaches minus 1 from the left of x squared plus a. And I'm going to specifically work with the left-hand side, and then we'll go back to the right-hand side. This function we are taking the limit of is a polynomial, and the substitution property tells us we can simply substitute in that minus 1. And once again, we should always justify the substitution property, so I'm just going to write a little SP to the side, indicating that we are applying the substitution property. And this will become minus 1 squared plus a, which is really 1 plus a. Now that we've taken care of the limit from the left, we need this quantity to be exactly equal to the limit as we approach minus 1 from the right. And when we are inputting numbers a little bit bigger than minus 1, x would be larger than minus 1. So in our piecewise defined function, we go to a minus x. So this would be the limit as x approaches minus 1 from the right of a minus x, which is also a polynomial. So using our same justification as we did to the left, the substitution property tells us simply substitute in x equals minus 1. And since we've already written down the substitution property, we'll just go with that same justification. If you want, you could rewrite it to the right-hand side, but I'm okay in this case if you do not. And this is equal to a plus 1. And what we need to do is solve for or find all of the values of a that make the limit from the left equal to the limit from the right. And no, 1 plus a is always equal to a plus 1, regardless of which value of a you might happen to choose. So note, this is true for all values of a. That is to say, irregardless of the choice you make for a, this function p of x will have a limit at minus 1. So some conclusion needs to be given. And our conclusion is that the limit as x approaches minus 1 of p of x is equal to a plus 1, and this is for any value of a. And I'm going to box this so that the answer is as easy as possible for any reader to see. And then part B of this question asks us, what are the values of a that will force p to be continuous at x equals minus 1? Well, let's just recall, what does it mean for a function to be continuous at minus 1? Well, the precise definition of continuity would be when the limit as x approaches minus 1 of the function is equal to the function value at minus 1. And note, we don't have to work too hard for that limit value at minus 1. That's precisely what we found in part A. That limiting value is always going to be a plus 1. And in terms of the function value at minus 1, that's where we need to use that middle part of this piecewise defined function. When x is equal to minus 1, the function is defined to be x squared plus a squared. So this is where we need to use that part of the function. So this would be minus 1 plus a squared, because we are substituting in x equals minus 1. And any value of a that satisfies this relationship would correspond to a value of a where the function is continuous. That is, we have an algebraic equation that we must solve. And I'm going to go ahead and throw all of my a's on one side, and because the coefficient of a squared is positive on the right, I'm going to leave it there for simplicity. So we need to subtract a and subtract 1 from both sides. And note, we have a quadratic equal to 0. You could use a quadratic formula. There's nothing wrong with that. That's always a great fallback option. But at the same time, note that this does factor quite nicely. This is a minus 2 times a plus 1. So there's two possibilities. A equals 2 or a equals minus 1. So our conclusion is the function p is continuous at x equals minus 1 only when a equals minus 1 or a equals 2. So just to conclude, this is definitely what I would consider to be an involved example, but hopefully now we've seen several of these examples and we have a very nice template of, more or less exactly what our work should look like and what it should include. So let me finish by encouraging you to work on problems 1 and 3 of that class worksheet. Check your work versus the solutions posted on Canvas. And also, do not forget about looking in the textbook, working through suggested problems. When you have questions, do not hesitate to reach out. Stop by office hours or drop me an email. So stay tuned and take care.